In this section of the book, we're going to talk about dynamic regression models. Now, we can think about this chapter as extending and bringing together earlier work. For example, in the regression setting, we are extending what we learned in chapter 7 and combining that with what we learned in chapter 9 of ARIMA models. So this framework now allows us to have exogenous variables, information about promotions, information about whatever exogenous factors we think might be affecting Y, together with richer dynamics of the ARIMA models in one framework. So a regression model, the typical regression model, multivariate regression model looks like this, where epsilon t is the error process, and we assume that epsilon t is a white noise process. What we want to do here is we want to extend this to allow for epsilon t to be autocorrelated. Here's an example where we have our regression model, but our regression model has a different error process, eta t, and this eta t now is allowed to have dynamics in it. Okay, and from these two, we do not assume that eta t is white noise. It has dynamics, is defined by the second equation here. What we assume is that this epsilon t that drives this second equation is the white noise process. And we're going to specify these and estimate them in simultaneously in one system. So let's delve a little bit more into that example. So our first equation here is a regression equation. The error process associated with this equation is the regression errors. The second process here specifies the dynamics of our regression errors, and the error associated with this one is the innovation error. So we need to make sure that we separate between these and we identify that we have two error processes. In ordinary regression, eta t is assumed to be white noise, hence eta t is equal to epsilon t. There's no more dynamics to account for. Now, if we go and estimate this equation, this regression model, assuming that eta t is white noise and it is not, then we have problems. So if we try and minimize the sum of squared errors, where the error is now autocorrelated, we have if the eta has some dynamics in it, we have estimates of the coefficients in the regression model which are no longer optimal. They're consistent estimators, but they're not efficient because some information is ignored. And anything to do with statistical inference, p-values, or model selection is actually wrong. There is one more complication, that if any of this eta t is non-stationary, then your estimators are not consistent. They're completely wrong, unless you have co-integration and stuff like that, which we don't get into this book. Now, if instead we minimize our error process of the second equation, which is the white noise process, then we avoid these problems. In this book, we don't minimize sum squared errors. We actually look at maximum likelihood estimation, which is similar to minimizing sum squared errors. We won't get into the sort of details of that. Now let's have a look. Let's start with a simple example or the simplest example, where we have stationary processes. So we have our regression model, but our error process is allowed to have some dynamics. Everything is stationary. We can go and estimate this, and we get consistent estimators, minimizing the error of the second process, and all is good. Now, if we want to estimate this and some of these variables are non-stationary, then our estimated coefficients, as I said before, are incorrect, and we need to deal with this. And the way we're going to deal with this in here is take differences of the variables to make all the variables stationary. So here's an example where we have a regression equation, and we allow for our error process, our regression error, to be a non-stationary process, and have some short-run dynamics. So we're going to have an ARIMA 1-1 process for this error, for the regression error. Now, what we can show is that we can take this and take differences of the equations, just re-specify a little bit and show that this second specification is equivalent to this first one. So what we do is take differences of the first equation. So instead of having yt, we're going to have yt dash, the difference of yt dash is equal to yt minus 1, as shown here. We difference all the x variables, making sure that we're the same order of differencing, and we're differencing the error process. So eta t dash is equal to eta t minus 1. Hence, our second equation now is in terms of this difference error, and this is a ARIMA process, an ARIMA 1-1 process. Notice that the parameters of these models are identical. So if we can't estimate this model, but we can estimate the second one and map back the parameters to the original problem that we were thinking about, to the original regressors that we were thinking about. So usually we refer to this first model as a model in levels, and this second model as a model in differences. Okay, so we specify this so because we want to show that this can be generalized, that any regression with ARIMA errors can be rewritten as a regression with ARIMA errors by differencing all variables with the same differencing operator as in the ARIMA model. So if in the original data, in the original setting, we had this model in mind, well, after differencing all variables, we get this model. So a lot of books will send you a warning in terms of estimating these, but you can estimate this model here, and these coefficients translate into these coefficients that you were originally interested with.